discussion section, it gets to be a huge pile and then make marks somewhere. I also will post the solutions to the first assignment on one of the bulletin boards over there. I don't want to do the second assignment because we know every week some people couldn't get it done and are still working on it. So the solutions, I think what I'll do is I'll always post the solutions 1 week after they were due. Listen, I butchered the very end of Monday lecture, and it's been on my conscience ever since. That I don't think that I was clear on the notation for integral calculus. So I want to begin today just by summarizing the notation. Maybe you picked it up from last time, but if you didn't, here it goes. What? The indefinite integral also known as the antiderivative it's written like this. G of t is the indefinite integral of, I don't want to use v and x because that's just a particular application, so I'm going to use g and f. G of t is equal to the integral of f of t dt. What does this whole expression here mean? It means that g is the function which, when differentiated, gives you f. It's the antiderivative of f dg by dt equals f. Parenthetically, it always includes an additive constant, a so-called constant of integration. Why? Because if you added a constant to g, it would give you 0 contribution to the derivative, because the derivative of a constant is 0. So there's always an added constant. In physical context, the added constant, the constant of integration, usually turns out to be the original position or the original velocity or something like that, some initial condition. Examples? Position is the integral of velocity. Velocity, in turn, is the integral of the acceleration. But in principle, you could have a million other applications for indefinite integral. That's the indefinite integral. Note it flagged by the absence of any numbers at the bottom and at the top of the integral sign. The definite integral is integral now with limits, so-called limits, t1 and t2 of f of t dt. That's nothing but g at the upper limit minus g at the lower limit. Geometrically, this is the area under the graph of f of t between t1 and t2. So f of t looks like this, graphed against t. This is t1.
Yeah, one of those has to be a t1.
Is that better?
Yeah.
Okay, graphically, it's the area under the curve. F of t. This tells you the area under the curve. Something very profound has just happened. This has told us how to calculate the area under any graph, whatever its shape is. What do? You anti-differentiate the function, dream up a function whose derivative is that, and then just evaluate it at the upper limit and at the lower limit, subtract the two, and that'll give you the area under the graph. That's essentially the fundamental theory of calculus. How do you calculate areas under a graph? That's the definite integral. How do you calculate the slope of the graph? That's the derivative. Example. The example of most importance to us, x of t2 minus x of t1 would be the distance traveled is equal to the integral from t1 up to t2 of v of t dt. So if you want to know how far an object went in a certain time t, and you happen to know what its velocity was at all times, you integrate that. This notation here means the indefinite integral. It just means the antiderivative. This notation here, with the two flags, top and bottom, that's the definite integral, and that means take the antiderivative, evaluate it at the upper limit, and subtract the value at the lower limit. Got a picture? Okay, maybe that was not necessary, but I just felt badly for how things have been left on Monday, and I wanted to make sure that I hadn't just totally confused you on that. Okay, now for something completely different. Vectors. Which the book, for some reason, puts right at the very beginning. Almost everything we've done so far, actually everything with the possible exception of projectile motion, has been motion in one dimension, moving along a single line. And projectile motion isn't really a good exception to that, because projectile motion, the two components, the horizontal and vertical, are totally independent of each other. So it's really a package of two one-dimensional motions rather than genuine two-dimensional motion. But anyhow, we want to generalize now from one-dimensional motion to two and three dimensions. This is very easy. There's nothing deep in this at all. But it does call for one piece of specialized notation, and that's vector notation. So what I'm going to do today is summarize all the facts that you need to know about vector notation. Let me introduce the problem like this. It's going to seem like a stupid example, but I think it's the essence of the problem, really. Suppose that you walk 4 miles due north. And then you walked 3 miles due east. You walked a total of 7 miles. But you didn't get 7 miles from where you started out. You're only 5 miles from where you started out. How does it come about that you can add 4 plus 3 and get 5? We need a notation for quantities like this that evidently don't add in the usual way. Now you know what the reason is. The reason is that displacements not only have magnitude, 4 miles, 3 miles, what have you, they also have direction, north, east, whatever. And you've got to take careful account of the direction as well as the magnitude when you combine them. If you want to know the total displacement, you need to know not just the magnitude of each separate displacement, but also what direction it was in. Obvious, huh? An object like displacement that has both magnitude and direction is called a vector. On the blackboard, we will write vectors as arrows. just as I did here. In fact, always, if you want to know how vectors behave, think in the back of your mind how displacements behave. Vectors, or the whole theory of vectors, is designed to mimic the behavior of displacement. But then in due course we discovered that there are other quantities that also have magnitude and direction. Velocity, I could have velocity this direction or velocity that direction. Acceleration too, that also is a vector. And later on, momentum, all kinds of things, quantities that have both magnitude and direction. But they're all built on the notion of displacements and this simple observation that if you make two displacements not in the same direction, then the total direction, total distance you went is the total displacement is not just the numerical sum of those two. Anyhow, we represent them as vectors, as arrows, excuse me, represent vectors as arrows. Of course, the length designates the magnitude. So this is a somewhat larger magnitude than this, of course, and good longer. Length designates the magnitude, and the arrowhead indicates the direction. If you're, oh, by the way, vectors have magnitude and direction, but they do not have location. What does that mean? You're allowed to slide a vector around as much as you want, provided that you never stretch it and you don't rotate it. It's still the same vector. This is the same vector as this is, provided that I drew it not and brought quite in the same, they're supposed to be pointing exactly the same direction, and they got exactly the same length. That's the same vector. Just as it's the same number, if I wrote the number 3 up here and the number 3 down there, you're not going to tell me that's a different quantity. It's the same number. Numbers don't have any location. Vectors don't have location either. They have magnitude and direction only. So you can slide vectors around at will, just don't stretch them or rotate them, and you still got the same vector. On a diagram, in an equation, in text in general, we represent vectors with a boldface letter, which I can't draw here, or just put an arrow on top. So, that would be a vector, or like that. Your book, leaving nothing to chance, makes some boldface and puts an arrow on top. That's overkill, but certainly makes a point. Now, what can you do with vectors? The rules of vector arithmetic. Arithmetic, or in some cases this is even just a piece of notation. Magnitude. How am I going to denote the magnitude of a vector? For example, this vector was 4 miles pointing due north. The due north part is the direction, of course. The magnitude was 4 miles. We designate that like this. With vertical bars there. Or, if it's not subject to any ambiguity, A with no vector sign on it at all, or not boldface if you're a typesetter. Folks, vector notation is very nice, very easy to work with, as long as you're disciplined. Can I beg you, always, if you're talking about a vector, stick an arrow over the top. I'm teaching a course right now at Mount Holyoke for junior and senior level electricity and magnetism, junior and senior physics majors. And about half of them in the homework I've seen never bother to put an indication that they're talking about a vector. I guess that you can manage to get through freshman physics, maybe sophomore physics, without being fussy about this, but it's going to burn you badly later on if you get in bad habits. I've got to know, the reader's got to know, is this thing you're talking about a vector, or is it not a vector? By the way, we need a word for not a vector, just for contrast, that is called a scalar. That's a quantity that has magnitude but no direction. So, the ordinary quantities that we usually would talk about are all scalar quantities. We're now introducing a new thing which has direction as well as just magnitude. If in your own writing you don't distinguish a vector with an arrow at the top, then you can never tell the difference between a vector, A, and its magnitude, or worse yet, some other scalar that may be floating around in the problem. Very bad. Two, minus a vector. What would I mean by minus A? That's a vector with the same magnitude but the opposite direction. I think that's natural. So if this is the vector A here, then the vector minus A, whoops. There's the vector minus A. Same length, opposite direction. Third item, addition. How do you add two vectors? Answer, you do it the same way that you would do it for displacements. This is built on displacements. How do you figure out the total displacement? Well, we draw the arrow representing the first one, and then the arrow representing the second one, put the tail of the second one at the head of the first one, and complete the triangle. That's the way I think of it. So, if I had vector A here and vector B here, and I wanted to construct the sum of those two, what I would do is slide B up until its tail is at the head of A, and then complete the triangle. Remember, this is the same vector B because I didn't change its magnitude or direction. I just slid it parallel to the original one. That vector there then is A plus B. Make sense? What if I did it the other way around? What if I did B plus A? Well, I might have taken a vector B and slid A over to its, so that the tail of B A hit the head of B and completed the triangle. I would have got exactly the same thing. Do you see that? Mm-hmm. In fact, some people prefer to think of it as a parallelogram rule. Here's A and B, and the sum of them is the diagonal of the parallelogram. And it doesn't matter whether you thought of it as A plus B or as B plus A. You're obviously come to the same place either way. Do I need to tell you how to construct the difference of two vectors, A minus B, how to subtract? I don't think so. A minus B would be A plus minus B. I know how to construct minus B, just draw the arrow with an arrowhead on the other end, and I know how to add those two vectors. So it would be to add A and to subtract B from A, I would take A, there it is, construct minus B, move it over. Here's A. Minus B would be that thing pointing in the other direction. Stick the tail of minus B at the head of A, and it would look like that. So here's B. Actually, that's minus B now, and this is the quantity A minus B. So you don't need a new rule for subtraction. It is addition of minus B. Make sense? That's actually the other diagonal of the parallelogram, if you like. Being a little bit careful here. Now this is A minus B. Going the other direction with the head on the other end would be B minus A. Okay, there's addition. There are now three kinds of multiplication for vectors. The first is fairly obvious. Multiply by a scalar. If you multiply a vector by a scalar, like the number 3 or something, that's going to give you a vector with the same direction but 3 times as long. Seems sensible? Multiply the length. But don't change the direction. Oh, unless the multiplier was a negative number, in that case you would flip the direction, of course. So multiply magnitude, don't change. Let's see, if that's the vector A, then drop down here, that's A, there's 2A. Twice as long, but same direction. Now, the more surprising ones. 2 ways that you can multiply vectors. First is the so-called dot product. The dot product of 2 vectors is defined as follows. And here, I'm not sure that I can motivate this particularly. This is what I'm trying to do is give you all of the arithmetic of vectors right now in one package. Later on, we'll come to the context where the dot product and then the cross product is actually useful for us. The dot product, in case you're ahead of the game, comes into physics in the first instance in the definition of work. Dot product, A dot B, big old dot, centered, not down at the bottom. A dot B, that's equal to the length of A times the length of B, the product of the lengths of the two, times the cosine of the angle between them. I'm going to put a box around that because that's probably the first thing that's actually new. A dot B is AB times the cosine of the angle between them. So if I had A and B here, here's A, and here's B. Theta would be the angle between them. Stick them tail to tail and mark off the smallest angle between them. That's the theta. Let me ask you a question. What if I took 2 vectors that are perpendicular and calculated the dot product of them? What would that be?
0.
0. How come? Because if they're perpendicular, theta is 90 degrees. The cosine of 90 degrees is 0. So that should put it right down here. A dot B equals 0. What if they were parallel? If they're parallel, then the angle between them is 0, and the cosine of 0 is 1. So in that case, I would get A dot B is just equal to the length of A times the length of B. For example, if you've got the dot product of any vector with itself, A dot A is just the square of the length. Finally, the cross product of two vectors is written like this. A cross B is equal to the length of A times the length of B times the sine of the angle between them times a unit vector of length 1, for which most people use a little hat on there to designate that's a special kind of a vector of length 1. And what direction does it point in? Perpendicular to both A and B. Let's think about this for a minute. If I've got two vectors, they define a plane, isn't that right? In general, they happen to be parallel, then that would be an exceptional case. But if they're parallel to one another, then the sine of theta is 0 and the sine of theta is 0, so the cross product is 0 anyhow. Two vectors would define a plane. Here are two vectors, A and B. I'm going to draw these so that they look like they're in the horizontal plane here. So that's going back into the board, and this is coming sort of out of the board. A and B going back into the board. And can I put the angle theta there so it looks like we're looking at that obliquely? Then the unit vector points perpendicular to both of them. The two vectors, A and B, define a plane. In this case, the plane of the table. The cross product points perpendicular to that plane. Uh-oh, there are two perpendiculars to the plane, right? Could be going up, could be going down. Both of those are perpendicular to this table. Which direction does the cross product point? I'll say it to you, and we'll have to pick this up again when we start using the cross product. The direction, I know that the direction is perpendicular to the plane defined by those two vectors, but which direction perpendicular, up or down? The answer is given by the so-called right-hand rule. Take your right hand, stick your fingers in the direction of the first vector, curl them around toward the second vector, then your thumb indicates the direction of the cross product. It's a mouthful, but let's see if I can write it down. Unit vector, magnitude 1, pointing perpendicular to the plane of A and B in the direction of the right-hand rule. Fingers along A, fingers of your right hand, of course. Your left hand, you're going to come out backwards. Fingers along A, curl toward B. Then your thumb indicates the direction of n hat. I'm sorry, it's nasty, but there you have it. So, for these two, A and B. Suppose that A and B are both in the blackboard. You tell me, what direction is the cross product A cross B point for these two vectors here, lying in the plane of the blackboard?
Into the board.
Into the board. Very good. A cross B. Stick your fingers in the direction of A, curl them toward B, thumb points into the board. How about B cross A?
Out of the
B cross A would be out of the board. It's the other direction, right? So general rule there, then, that B cross A equals minus A cross B. One final point. The dot product is itself a scalar. It doesn't have any direction. The cross product, on the other hand, is a vector. The cross product is a vector. By the way, what's A cross A? If you take the cross product of a vector with itself, what are you going to get? 0, right? Because that's the case where theta is equal to 0, and therefore sine of theta is equal to 0. Maybe I should put this down here too. A cross A is always equal to 0. Okay. All of the arithmetic of vectors is now on the table. We're going to be using all of it up to 4 right away. 5 comes in the next unit when we start talking about work. 6 comes in when we start talking about rotations. One last thought. When I was in high school, I was taught about 16 different rules, especially in electricity and magnetism. Right-hand rules, left-handed rules. There was a 3-finger rule for something or other. I don't even remember. And you know, you always had to remember which finger is representing what in what context. There is only one ambiguity to be resolved. There's the difference between a right-handed screw and a left-handed screw. That's essentially what the right-hand rule is doing for you in the form of in defining the cross product. That's the only ambiguity. All of those other rules, if they're still doing that, left-hand rules and right-hand rules and all that stuff, it all can be reduced down to one single rule and soaked up in the cross product. So personally, the situation as far as directions got a whole lot simpler when I got to college, because all of those different rules became just a single rule, the rule for calculating cross products. I don't know if that's a relief for you or not. Now, so I've told you all of the rules of arithmetic in what you might call the abstract form, but it's actually very difficult to communicate to somebody. Suppose that I want to tell you about a vector. Vectors live out here in space. How am I going to tell you this particular vector? Well, I could say it's about 18 inches long, and it points toward the exit side from some turkey's right elbow who's standing, well, about 3 feet from the desk here, and his elbow is about 4 feet up. Understand the problem? Communicating magnitude is trivial. I just tell you the length of the vector. But communicating direction is, in general, very awkward. It doesn't pay to do business this way. I mean, geographically, we could say, you know, 37 degrees east of north or something like that. That's not too bad, but that's just 2 dimensions, right? What if it had a vertical part to it? Also, there's a much better way to communicate about vectors, and this is in component form. The idea of components is first lay out a coordinate system, a Cartesian coordinate system. So in the corner of the room, I'm going to start with the origin there, and I have my z-axis run straight up, and the y-axis run along the wall, and the x-axis come out like this, let's say. So here are the 3 axes. this language because I never said anything about particular coordinates. Mathematicians tend to really dislike coordinates because they say, that's perfectly arbitrary, you know? Somebody else might come in here and lay out coordinates a different way. My reaction is, yeah, more power to them. As long as we understand what coordinates we're using, everything is from then on unambiguous. Mathematicians say, yeah, but I don't like it to be dependent on somebody's arbitrary choice like that. Well, if you're at that frame of mind, then all of this stuff over here never made any reference to what coordinate system you've chosen. Everything we do now is going to make explicit reference to a particular arbitrarily chosen coordinate system, but even mathematicians, you ask them how they actually do problems, first thing they do is set up a coordinate system and start doing it that way. So, anyhow, here's x, y, z, and here's some vector, a. I want to specify a using those coordinates in the following way. My idea is this. Let's drop a perpendicular here so that we know exactly where this point A is. Got a picture? I'm going to go out the x direction a certain amount, a sub x, and then I'm going to run along parallel to the y direction, a distance, let's call it a sub y, and then I'm going to go up parallel to the z direction, an amount, we'll call it a sub z. And when I've done that, I will have arrived at the head of A. So why don't I, instead of saying the vector A has a magnitude of such and such and it points at 37 degrees from the z-axis and so on, why don't I just tell you these three numbers, a sub x, a sub y, and a sub z, and that would do the job, isn't that right? Because then you know the ritual. You go out the x direction, amount a sub x, parallel to the y direction, amount a sub y, parallel to the z direction, amount a sub z. You can do those obviously in any order you want to, and that would specify uniquely what this vector A is. So, specify A by giving what are called the components of A. A sub x, a sub y, a sub z. Some people will actually put these in parentheses, and that triple of numbers is just a nice way of telling you what vector I was talking about. Of course, as mathematicians will say, you've got to know what direction the x-axis pointed in the y direction and the z direction before this means anything at all. Somebody else looking at exactly the same vector, but using a different set of coordinates would assign three totally different numbers. Well, big deal. We're going to stick to a particular set of coordinates, and with respect to that coordinates, this now very cleanly specifies the vector A. Do you agree that those three numbers would do the job? Now I know exactly what vector we're talking about. Of course, if the vector was sitting up here originally, I would slide it down so that its tail is at the origin first, but I can always do that. Actually, it's traditional to introduce at this point three unit vectors. So unit vectors pointing along the direction of the three coordinate axes. Unit vectors, which for some reason, don't ask me why, are called I hat, j hat, and k hat. Those are unit vectors, meaning, remember, length 1, pointing in the direction of the x-axis, in the direction of the y-axis, and in the direction of the z-axis. So, can I put it on this same diagram? Here's I hat, here's j hat, and here's k hat. Unit vectors pointing in those three directions. And now another way of writing the vector A, instead of just giving the triple of the three components, is I could write it like this. I was hoping to keep all of this stuff on there. I guess I can't do it. Never mind. A I could write it like this. A sub x, that's the x component in the I hat direction, plus A sub y in the j hat direction, plus A sub z in the k hat direction. Some people, as I say, will just hand you the triple of these numbers. That would do the job. Some people prefer to write it out in what is actually the notation of vector addition. I construct a little vector that's pointing in the x direction and whose magnitude is A sub x, and then I add to that a vector pointing in the y direction whose magnitude is A sub y, add to that a vector in the z direction whose magnitude is A sub z, and I've constructed a vector. So that's sort of in a constructive way exactly what I was saying here with the red line. Walk out the x direction, add a vector in the y direction, and add a vector in the z direction. So far, so good? Yeah?
You have to have the x, y, and z because isn't that what the I, j, and k mean?
So what are you proposing? That I could take the x off here,
X, y, and z.
but then these would all three look the same, right? This is, A sub x is this length here, that amount. The amount I have it. A sub y is this completely different length, the component along the y direction. And A sub z, the height I have to go up. So I dare not take those subscripts off. What bothers me is, why do I say A sub x I hat? Why didn't I say A sub x x hat? That would make much better sense, notationally, I think. Or maybe A sub I hat, that would be fine. But to me, this notation is very traditional. You can't get away from it. All the books do this. But it just seems funny that the unit vector in the x direction is suddenly called I. Why I? You know, and in the y direction it's called j. In the z direction it's called k. So there's the component way of writing, the way of writing a vector, specifying a vector using components and the three unit vectors. Now let me list all of the rules of vector arithmetic in component form. Everything that we did before, you know, putting the tail of B at the head of A and completing the triangle or something like that, there's another way of saying that in terms of what happens to the components. And that's what I'm about to do. Actually, it can be very powerful to use the two different representations back and forth, knowing that there are two different ways of thinking about each operation, depending on whether you want to do it in component form or abstract form. First of all, magnitude. Remember, that's what we're writing A like this. If I told you the three components of A, do you know how to write down the magnitude of A? If it was 2 dimensions, I'm pretty sure you do. If I had A sub x here and A sub y here, and I said, okay, what's the magnitude of that vector? How would you do it? Well, no, I'm talking about the magnitude.
Ax squared plus a y squared square root.
Square rooted, yeah, the Pythagorean theorem, right? So this would be, in this case, it would be ax squared plus ay squared, according to Pythagoras. Now, you may not know this, but you can actually prove it to yourself very simply by doing the Pythagorean theorem twice. That if you have 3 components, like this, the length of the whole thing is the square root of the sum of the squares of all 3. So it would be ax squared plus ay squared plus az squared.
It's probably worth it to draw the length in a 2-dimensional plane.
Indeed.
X, Y. That shows how you can do it.
That's the proof. Thanks, sir. Draw that line there. I can get that in terms of ax and ay using the Pythagorean theorem. It's ax squared plus ay squared. And now look at this right triangle here. One side is az, the other side is root ax squared plus ay squared. To get the length of this, you want the sum of the squares of this plus this, but the sum of the squares of this is ax squared plus ay squared plus az squared. Take the square root. Very cute. So now to prove it. This is Pythagoras applied twice. Minus a, that was the second one. In terms of components, what does that do? Just switches the value of each component. That's pretty clear. Instead of going in the positive direction, you go in the negative direction. Third, addition. If I had two vectors, and I've written them out in component form, a plus b, what would the components of the sum be? Answer, just add like components. Ax plus bx in the I hat direction, ay plus by in the j direction, plus az plus bz in the k direction. The rule is add like components. That in component form says exactly the same as stick the tail of the second vector at the head of the first vector and complete the triangle. It's exactly the same. Gives you exactly the same result. 4 multiplied by a scalar. In the component form, what would I mean by c times a? Remember that just extends the length of the vector by a factor of c, not changing the direction. It simply multiplies each of the components. Multiply each component by the scalar out in front. 5. Now a nifty one, the dot product. Remember, the dot product of two vectors was the magnitude of one times the magnitude of the other times the cosine of the angle between the two. What on earth does that say in terms of the components? Not obvious, but let me write the answer, and then maybe we'll talk about it more next time. The answer is that a dot b is equal to ax bx, the product of the x components, plus ay by, the product of the y components, plus az bz, the product of the z components. So I won't write this out in words, but it is the sum of the products of like components taken from the two vectors. Make sense? I'm not sure that it does make sense. Next time I'll run a bunch of examples involving that formula there and the original version. You'll notice that I did not tell you how to calculate the cross product in component form. Very good reason for that. It is ugly. So we'll do that when we absolutely have to, but not before. Remember, if you didn't pick up your papers, graded papers,